composite beams, and our focus really is on the analysis and the design of these composite beams. So let me share my screen just so that we can just pick up where we ended last time. So we covered this example last time. If you were to recall, the question here, it was, if we can just read the statement. So it said that determine the bending stresses for the composite beam shown in this figure. The beam is a composite steel concrete section, and we introduce a grade there. We said you need to use a grade S355JR steel with a concrete with a 28-day compressive strength of 20 MPa. The beam is subjected to a bending moment of 150 kilonewton meters. So that's the statement that we gave, and then obviously the beam cross section is given this way. So if you look into the beam section that we have, there is an I section as the bottom of this beam, and there's a concrete section on top, or the concrete slab, and the dimensions of the concrete slab are given. And what we decided to do is to use the modular ratio to be able to transform this section. And what we mentioned is that the modular ratio is given as N. So this N is equal to ES over EC, which is the modulus elasticity of steel divided with the modulus elasticity of concrete. And when you divide the two values, you get a value of 8. And now, if you take the original width, which is 1,200, and you divide that by 8, then you get a value which is equal to 150. Then using that 150, it will mean that the width of the concrete section is actually equal to 150. There's a hand that is up.
Good afternoon, sir.
Hi.
Can you hear me?
Yes, I can.
Okay, sir. Sir, I have a question on this question that you're displaying.
Yes.
And my question, sir, is that I was working through the example myself,
Mm.
and I wanted to ask you, Guru, where did you find the 15,000? Because on the steel table that I have, the area of the steel is 6.82 10 to the power minus 10 to the power 3. I'm not so sure if I have the correct one. This is the one that we were using for steel design. No, finally.
Yeah, the 6.2, 6.82 that you are referring to is here. Is that the value that you are finding?
Yes, I got 6.82, but the other area, the area of
Which one?
15,000, the area of 15,000.
That's a rectangle. To calculate the area of a rectangle, length multiplied by breadth. 150 multiplied by 100.
Oh, okay. I understand, sir.
Okay.
Thank you, sir.
All right. Speaking of areas, obviously you have to divide this shape into two, because there's a bottom shape that is made up of steel, and there's a top shape that is made up of concrete. So you can say then shape number one is the steel shape, and shape number two is the concrete surface. And then what we can do then, what we did actually, is to use the table to simplify our analysis. So we divided this into two shapes. Then for each shape, we can be able to find the area, And after finding the area, then we can be able to calculate y bar for each shape. So what we did that, and then we calculated AY. And then after finding AY, we found the total of AYs, we found the total of areas. And if you take AYs and you divide AYs with the areas, then that is how you can be able to get the centroid. So we got a value of the centroid then to be equal to 296.52. That's the value for the centroid. And this is if you are taking the centroid from the bottom part of this section. But what we mentioned is that you don't have to always do that. You can take the centroid from the top of this section as well. So you can decide to take the centroid from the top part of this section. And when you do that, then the value that you're going to get is 114.38. Both these values, they are moving from the surface to the neutral axis. So you can see that they are finding this value of the centroid, then we are able to find the position of the neutral axis. So the position of the neutral axis is located there in between those two, the two centroids. So this is what we had. And from there, then after finding those values, then we continue to find IXC, and we found the value of D, and then we find the value of AD squared. And the reason for that is because we wanted to use the parallel axis theorem, where we can calculate IXX to be equal to IXC plus AD squared. So the total of IXC was 129.5 times 10 to the power of 6, and 80 squared is 197.89 times 10 to the power of 6. So this is what we did. Is that an old hand or is it a new hand? I see there's a hand that is raised again. Okay. All right. Let's continue. So what we can be able to do is well, we are having this section. Maybe if one were to draw this section again that we have we have this composite section where the bottom part of this composite section is steel, and this steel is made from I section. So this is steel that is made from I section. So this is the I section. And then on top of this I section, we have a concrete surface, and there is this concrete slab, and this slab has reduced. The width of this slab is now equal to 150 millimeters. The height of this slab is equal to 100 millimeters. There's also height of this I steel section. What was the value of the height here?
I think it's
Yes,
310, 310.9.
310.9 millimeters. Thank you. So that's the height of this steel section. And what we were able to find, we did manage to find the position of the neutral axis. So this line here, this is giving us the neutral axis. That's the position of the neutral axis. So now we did calculate the distance from the bottom to the neutral axis, and there's the distance that we calculated to be 296.52. So we said this distance is 296.52. And then there's another distance on top, which is 114.38. So if we measure this from the top side, then this distance is 114,38. So that's the distance that we have from the top side of this neutral axis. So this is what we that's what we have. So, and it's very important that we find this neutral axis because yeah, maybe let me ask you, what's the importance of the neutral axis? Question. Why is it important that we find the neutral axis? What's the importance of the neutral axis? Hello?
Answer.
Uh,
Yes.
Can I try?
Yes, you can try. You almost you always more than welcome to try in this class.
Okay. From what I know is that the neutral axis help us to determine which side of our structure is in compression and which side of our structure is in tension.
This is true. This is true. This is why we will find the position of the neutral axis. Then in that way we can see which structure is going to be in tension and which part of the structure is going to be in compression. So what we can be able to also find here is the bending stresses. So these bending stresses that we're talking about. So we can be able to find these bending stresses. And if you were to recall, we mentioned that to calculate the bending stress, you use the Fletcher formula. Sigma is equal to my over I. This is how you can be able to calculate the bending stress. And we can find the bending stress really in any part of this section. So the first part that we can look at, we can calculate the bending stress at the bottom of this of the steel of the steel flange. So we can calculate the bending stress as the bottom of the steel flange. And the calculation of this bending stress, let's call it sigma 1. So the calculation of sigma 1 is really a calculation where we use my over I. That is what we will do. So the value of m in this question is given. So the bending moment is given as 296,52. So which means that this value then is 296,52 times 10 to the power of 6. Sorry, where am I taking this value? It's not 296,52. Sorry. It is it's 150. You guys are quiet. We are not just copying this down. The bending moment is 150 from the question. So it is 150 times 10 to the power of 6. That's the bending stress. And then we divide by the value of I. Well, the value of I, we calculated this value to be 327,39, 327,39 times 10 to the power of 6. 327,39 times 10 to the power of 6. And then we multiply that with y. Um, this y, this is where I need you to come in now. What will be the value of y here when we are looking for the stress at the bottom of this steel? Yes,
296.52.
That's correct. It is going to be a value of 296,52. Because remember, how did we define this I, this y? This y is the distance from the neutral axis to the position where we are looking for this bending stress. So from the neutral axis to the position where we are looking for the bending stress, the value is 296,52. So then we can be able to do this calculation. Can we all calculate this value and let's see what we get? What value are you getting?
135.86.
135,86 MPa. That's the bending stress. So we can highlight this value because this is just one of the stresses that we can be able to find. We can continue with this and find the stress on top of the steel flange. So we can find stress on top of the steel flange. So finding the stress, let's call this sigma number 2. Again, you can use the same equation, my over I, when we are looking at the top of the steel flange. Well, the bending moment is going to remain the same, so we're still going to have 150 times 10 to the power of 6. And I is also going to remain the same, which is going to be 7,39 times 10 to the power of 6. And then the value that is going to change is the value of y. What's the value of y that we're going to use now in this case?
I think it's 14.38.
14,38. How did you get 14,38?
I took the height of the flange, then I subtract
Mm-hmm.
by the value of y, which is 296.52.
Which is 296,52. I agree. So because if you look, the position of the position two that we are talking about is a position that is somewhere here. So which means that we are looking for this distance from here to here. That's the distance that we are looking for. Position one is and here is the bottom of this steel flange. So when you do this calculation, what value of stress do you get then?
6,59
Yes.
MPa.
6.59.
6,59 MPa. Thank you. So that's the bending stress that you will get then when you calculate the bending stress as position number 2. Then we can go to concrete now. So let's call this number 3. We can calculate the bending stress at the bottom of the concrete slab. The bending stress is the bottom of the concrete slab. Let's call this one sigma number 3. Sigma number 3 is equal to my over I. Again, in this case, m is going to be the same, which is 150 times 10 to the power of 6. And then you divide this by I, which is going to remain the same, 327,39 times 10 to the power of 6. Again, y not sure whether it's changing or what, but we need a value for it. Bottom of the concrete slab. Yes. The value of y
Is it 14.38?
14,38. Because if you look into um if you look into this position, so the position 2, it's the same as position 3, really. So the top of the steel flange is the same as the bottom of the steel flange. I know someone is saying, so now Sandila, why are you calculating the stress again if it is in the same position? Are we going to get the same answer? Think.
Nope, sir. We are not.
We are not, because
To multiply by 1 over n.
we have to multiply the 1 over 8. We have to multiply this one by 1 over 8. Don't ask me, where did you get 8? Can I use 7? No, can't use 7. This 8 is coming from the modular ratio. Our modular ratio is equal to 8. So this value of n is equal to 8. So this is why then we are multiplying by 1 over 8. That's what we have. Okay. So what's the value then are we going to get for this one?
0.82 MPa.
0,82 MPa. Okay. So that's the stress that we have as the bottom of the concrete slab. Let's look on top of the concrete slab. So let's find the stress as the top of concrete slab. We can call this sigma 4, which is my over I. Well, m is going to remain the same, so we're still going to have 150 times 10 to the power of 6. And you're going to divide by I, which is 327.9 times 10 to the power of 6. Let's multiply this by y. Is y changing? What's the value of y do we use here?
114,38.
I agree. 114,38. And then don't forget to multiply by 1 over 8. What is the answer that you get?
6.55.
6,55. 6,55 MPa. So this is the value of sigma 4. Is this not responding now? No. Okay. I want to highlight this value. So this is 6,55 MPa for sigma 4. So this is what we have. So these are the stresses that we have, and we can actually draw a stress distribution diagram for all these stresses. We know that we are dealing with a triangular stress distribution diagram, and drawing this really shouldn't be a difficult task. So we can start here at position 1. We know there is a value of stress there. that is 135,86. 100 135,86. That's the value of stress that we have there. And then its position 2 on top of steel flange, we're at 6,59. So which means that we go all the way to the top of the steel flange. So if we go up until the top of the steel flange, we know that we're going to reach a value of what is this value again? 6,59. So we're going to reach a value of 6,59. In the same position, the stress is changing to 0,82. So this stress is reducing again to 0,82. And then on top, then it goes back it goes back to 6,55. So which means that's the value that we have here on top. It is 6,55. So this is the stress distribution diagram. Okay, see there's a question, yes?
No, I couldn't see the screen, but now I do.
Oh, okay. All right. Okay, can we move on from this example then? Yeah. So let's just continue then with the textbook. So yeah. So then if we continue after this example, so we are being introduced to what is called the ultimate strength approach. This is another approach that one can be able to use to analyze composite schemes, um, which is different from the approach that we've been using. Um, the approach that we've been using is what is called the ultimate strength, elastic strength approach. So I think it was mentioned somewhere here on top. Where is it? Yes, here. So you can see this approach where we are using transform section method, we call it elastic strength approach. And the approach really is what we've been explaining, that we use the method of transform sections where we generate a mathematical model of being composed of different materials and transforming it into a section having uniform material properties. And then we'll go through the whole thing of changing the width of the concrete section, and then we transform it into a width that reflects the ratios of the modulus of elasticity, and yeah, so we explained that, and the fact that the only thing that we change is the width. We don't change the height, so that the stresses in the transform sections can just be calculated using Fletcher formula. And we don't also change the strain profile. And also, yeah, we don't change the bending moments of the structure. So that's the elastic strength approach. So what we are seeing now here is another approach, and this approach is called the ultimate strength approach. So this ultimate strength approach is actually the approach that is adopted by the code. So SANS at 10162 has actually adopted this ultimate strength approach for design of composite beams. So, and the ultimate strength state is achieved in a composite beam in the same manner as in a reinforced concrete beam. So the same way we are able to achieve this in a reinforced concrete beam, we are also able to achieve this ultimate strength even when we are dealing with a composite beam. If you were to recall, when we spoke about or when we went through reinforced concrete beams, so the reinforced concrete beam analysis is a very simple analysis. RC beam, it's a very simple analysis. So if you were to think of a rectangular cross section of a beam, where we are having this beam with different dimensions, and we can have the dimension here on top, which is that we can call B, and we can have a dimension here that we can call the height of this beam section. And obviously, this beam can be reinforced by reinforcing bars here as the bottom. And if we measure the distance from top to these reinforcing bars, then this distance we call this the effective depth. So that's just the cross section of a rectangular concrete section. And obviously, if this is a rectangular cross section, then finding the neutral axis is really easy. So the neutral axis is somewhere here. This is where the position of the neutral axis is. And from this, we can actually be able to draw the stress distribution diagram. Stress distribution diagram. So we can be able to draw the stress distribution diagram, and the drawing of the stress distribution diagram is not a difficult task. We know that the distribution of stresses from this section is going to be in parabolic shape, where we're having maximum compression stress here on top, and then we're having stress that goes all the way to a zero here, because this concrete doesn't carry any stress in tension. So yeah, this is the stress distribution diagram. So here on top, then this is where you will have the maximum concrete stress. And obviously, you can define a distance here from top to the neutral axis, and you can call this distance x. And this stress diagram is actually, you can see, it is a parabolic stress diagram. So it's parabolic stress diagram, and that's the actual stress diagram that represents the distribution of stresses here. But for simplifying our analysis, we don't usually work with this parabolic shape. So what we have done is we've said, okay, we can have an equivalent representation of this parabolic shape, where instead of representing it as a parabolic shape, we represent it as a rectangular shape. So we represent this as a rectangular shape, where here on top, we are still having our maximum concrete stress. But then obviously this distance is no longer x. Now it is reduced x. And how we reduce this x, we just reduce it by 10%. So that's the new distance that one will have. And so this is a stress distribution diagram that we can be able to work with. We call this one just an equivalent stress distribution diagram, or rectangular stress distribution diagram. This is what we have, and obviously there are forces that are experienced here due to this reinforcing tensile reinforcing bars. There's a tensile force here that we can call T, and then due to this concrete, there's a compression force here that we can call C. This is what we have, and um, we also know that there is equilibrium of these forces. So we can actually have equilibrium of these forces, because um, the equilibrium exist here. So which means there's the forces that are towards the right must be the same as the forces that are towards the left. So we can just say this tensile force is exactly equal to the compression force. So this is what one can be able to say. And calculating these forces also, it shouldn't be a difficult task because we know that from our strength of materials, stress is equal to force over area. So when I want to find the force, then I can just take the stress and multiply stress with the area. So for instance, if I want to find this compression force, then this compression force will be the stress in compression. And in most of the time, this stress in compression is actually FCU. And then we multiply this by the area. And the area there is, you can see, is B multiplied by 0.9. So we can say B multiplied by 0.9 multiplied by X. That's the area. This CU, we will usually multiply it with a factor of 0.67. So that's the factor that we usually use. By the way, we use these factors a lot in our design. I'm sure it's not for the first time you come across such factors. Maybe someone can remind us why do we use these factors? Or maybe we can ask with this one. Why don't we just say FCU? Because we know there's the 28-day compressive strength of concrete. Why do we multiply it by 0.67? Anyone? Well, we will multiply by guys, don't be quiet as if you didn't do design. Remember, guys, you've done design before, and we are building up on the design that you have done already. So we need those things that you learned. So these factors or this factor of 0.67, the reason we are multiplying this stress with this factor, it is because, remember, this 28-day compressive strength of concrete, we get it from crushing concrete, and this happens in the lab. So now, but then we use this concrete on site. So, and there might be differences between the strength that we test in the lab and the strength that we'll have on site. And to account for these differences, then we use these partial safety factors for the materials. Because when you test for material properties, you just pick samples, but then there might be differences between those samples that you pick and the strength that you actually have on site. So we do need these partial factors then, so that we can make sure that our accurate. So these factors are very, very important. And the code books also, they do give us these factors if we need to know if we know the material, then we know what's partial safety factor we can multiply with. So this is normal concrete. This is normal concrete. Oh, another thing that we can do with this normal concrete, we can take moments. And remember how we can take moments. We can choose the line of action where we are taking moments. So we can take moments about that force there, which is T, or we can take moments about that force there, which is C. So it's really up to us where we want to take those moments. So if we were to take moments about T, then we know that to get M is just going to be equal to this distance, this lever arm, which we can call Z, multiplied by the force of C. So it's just going to be equal to C multiplied by Z. This is how we can calculate this bending moment. And if we know that the force of C is actually given by 0.67 multiplied by FCU, multiplied by B multiplied by 0.9x, then multiplying this with Z is what is going to give us our moment. And this is our ultimate moment or our moment of resistance. So we can be able to find the moment of resistance then for this section just by using these forces there. That's in our free body diagram. That's the analysis of reinforced concrete beams. A normal reinforced concrete beam, a normal rectangular reinforced concrete beam. I know someone is saying, but Sandila, I thought we were dealing with composite beams here, not normal reinforced concrete beam. It's fine. Let's go back to composite beams then, because I see there are people who can't wait to see what happens then when you deal with the composite beams. So as we mentioned that these ultimate stresses, ultimate strength, ultimate moments, they are still found in the same manner as in a normal reinforced concrete beam. So we still use the same thing. So which means that if we have a beam that has steel as the bottom and concrete on top, then we can draw the stress distribution diagrams, and we know that also there are forces there that are being applied. There's a tensile force as the bottom of this section by steel, and there's a compression force at the top of this section by concrete. So we know that that is very important. And then it says here, I think it's important that we read these paragraphs, so that we don't miss these important things here. So it says here, the moment of resistance, the moment of resistance of a composite beam is calculated using an effective width. We are being introduced to something that is called effective width. I know that from the sessions that we've had, you know about the new width of multiplying by the modular range. That's not the one that we are talking about here. We're talking about effective width. And for us to understand this effective width, we need to go to SANS 10162, clause 17.4.1. I do. Maybe I can give you a second to also go to that clause. SANS tends to clause 17.4.1. If you go there, it says design effective width of concrete. So maybe reading is from here. So it says this. So the SANS code specifies the effective width of an interior beam as the minimum of 0.25, the span or the average of the distance from the center to center of the section to the center to center of the parallel adjacent parallel support, clause 17.4.1. Very important clause, because we need to be able to understand about this effectively. So here it speaks of interior beam. So it speaks of an interior beam. And so, and then it says clause 17.4.1 deals with the interior beam. I like how it's stated from the code book. So if you go through the code book, it says the flaps or cover flaps standing on both sides of the steel section shall be deemed to have a design effective width B equal to the lesser of 0.25 times the composite beam span. That's the thing. And then it says, or the average distance from the center of the steel section, truss or joist to the centers of adjacent parallel supports. So there are two things that you can have here. So we speak of an interior beam. There is also what is called an H beam. So if we are not having an interior beam, then we are having an H beam. Then we can be able to find this effective width, effective width of the section of the section, or let me just say effective width. So we can be able to find this effective width. Um, that's what we can be able to do. Maybe just to visualize these beams. But remember, we are dealing with composite beams. And what we are saying with these composite beams is that, so when we do composite design, we will normally have a steel section here as the bottom. I think it makes sense to have steel as the bottom because we know that when we have a beam this way, then the bottom is carrying tension. You need steel to be the one that is carrying tension. And then on top of this beam section, you have concrete. So, which means that we are having a concrete slab here on top. That's what we have. So that's the composite section. So a steel beam and a concrete slab. But what happened is this steel beam can be inside um let's say a structure. This steel beam can be inside a structure. So meaning that you can have another slab this side. You can have another slab this side where you are having another composite beam. Again, you can have I section here to carry tension. Okay. You can also have steel on the other side as well, or a beam on the other side. So the structure can continue this where you're having your steel beam cross section on this side. That's what you can have. And when you have something like this, then this beam, the beam that is in between, that is what we refer as interior beam. I see that there's a hand that is up. I thought I was simplifying things with this diagram. I wasn't bringing confusion. You can ask.
No, it's not a question. I just can't see the screen.
Oh, you can't see the screen.
No, I can't on my side.
Is there anyone who can see the screen by the show of hands? Okay. If someone can see the screen, then something might not be right with your network then.
Sir, I'm also unable to see your screen, sir.
Oh, you're also unable to see my screen.
Yes, sir.
Okay. Then if you also can't able to see my screen, then the problem is my network. Let me stop sharing. And then let me share again. Can you see something?
Yeah, now I can see.
Hello? Oh, now you can see. Oh, okay. All right. After explaining so much, you guys couldn't see my screen. Um, I I hope you understood the explanation for the interior beam and the exterior beam because I was explaining. Obviously, interior is the one that is inside, and exterior or edge is the one that is on the edges. So that's what we mean. So I think that this beam here will be what we refer to as an edge beam. Uh, are we all able to see what we mean by interior beam and an edge beam? So this one is interior beam and this one is an edge beam. So now the calculation of this effective width, it gives us conditions. So it says that for an interior beam, so if we want to calculate this effective width B, so if we want to calculate B when we are dealing with an interior beam, this B is the minimum value of what? So again, reading from the code, it says that it is the lesser of 0.25 times the composite beam span. So which means that we can take a 0.25 and multiply this with L. Or there's another 0.25. It's actually 0.5. The average distance from the center of the steel section, truss or joist, to the center of the adjacent parallel support. So when it says from the center of the steel section, so we actually speaking about the distance from center to center of these two steel sections. So the distance from here to here, if we can call this distance C, and this distance from here to here, we call this distance D. So that's the average distance that we want. So it is C plus D divided by 2. So that's how we can calculate this effective width. And then for edge beams, clause 17.4.2 from the code book. Again, there are two conditions there when you are dealing with an edge beam. So this B is the minimum value between two. Which values are we talking about? So the first value is it says that okay, it says slabs or cover extending on one side only of the supporting section or joist shall be deemed to have a design effective width B not greater than the width of the top flange. So we need the width of the top flange, and we know that this dimension of the width of the top flange is BF. So which means that for for the first part, then we know that we are dealing with BF, and then we add something to BF. And then for the second part, we are also dealing with BF here, and then we add something to this BF. And from the code, the first part is 0.1 times the composite beam span. So it's 0.1 times L. I can see the hand, this is up. Let me just finish writing. And for the second part, then it is 0.5 times the clear distance between the steel section. So the clear distance between the steel section is this distance that we have from these two steel sections. And this distance, we can call it C1. So then what we can say is 0.5 multiplied by C1. I see a hand. This is up. Uh, did you lose the screen again?
Yeah, your screen keep freezing.
Same here.
Um, Apologies, guys. Uh, Let me try to share again. Can you see? Can you see those conditions that I wrote there?
It's still loading. It's still black. Still loading.
Sure. Okay. How about now?
I feel the same.
Um, Okay, no, it's fine, guys. It's okay. We're gonna stop here today. I will when we meet next time. I will start from explaining this concept of effective width, I just wanted you to see what I was writing before you go, because this is important. I'm going to try to share again.